Hi everybody. We're here at the Graphio Universe, and not too subtle introduction to Neo4j webinar with our Big Things community. My name is Demi Ben-Ari, and we have in the background Shlomi Hassan. We're the organizers of Big Things. And I'm really pleased to be hosting Dr. Jim Weber, the chief scientist at Neo4j Technologies at our community. And I will let him to introduce himself, but I will start off with a small point that we have a questions pane in the webinar, and if anybody wants to ask a question for Jim to answer afterwards, just write off the questions and we'll try to answer most of them during the webinar. If you'd like, you can write it at the Facebook group as well or in the meetup, and we'll try to answer as many questions as we can. Jim, are you with us?
I certainly am, Demi.
Yeah, great. So I'll let you have the stage, as we say.
Thank you very much indeed. So, hello everyone. My name's Jim Weber, and I'm chief scientist at Neo4j. When Demi invited me to speak at the meetup, I wondered what the right tone was for an Israeli tech meetup. And having spent some time in Israel and knowing what a bunch of shy people Israeli technologists are, I thought we would have a very unsubtle introduction to Neo4j. So be prepared for as Israeli a presentation as an Englishman can possibly give. So, where are we? Well, we live in a very interesting world, I think. We live in a world where data has been revolutionized in the last decade. We have long since become used to the hegemony of the relational database. But over the last decade or so, we've seen the emergence of a number of alternative databases bundled under the NoSQL umbrella. I think these databases kind of really fall into two categories. Those where we denormalize data with respect to relational databases, those that have a richer model than the relational database. And those databases where we denormalize, we're quite used to using them. They're things like Cassandra or Riak or MongoDB, where we take data and we aggregate it into documents or keys and values or columns or whatever it happens to be. And the benefits of these kind of data models are that the data model itself is very simple. We can all quite conveniently deal with hash maps. And they're also amenable to a kind of MapReduce style processing. On the flip side, if we go down the right-hand fork in Alistair Jones' relational crossroads, we find the databases like Neo4j, the graph databases, those databases that actually have a far richer and more expressive model than we're used to in the relational world. And in this world, we're used to dealing with highly connected data, natively connected data. And the power of these databases comes from the fact that they're very expressive, and the technology enables extremely fast traversals of the graph structure. So therefore, for webs of interconnected data versus the denormalized stores, which have very denormalized, disconnected data. And this evening, I hope to persuade you that the transition to the right-hand fork in the road, to the richer model using connected data, is not at all difficult and is in fact pleasurable. Now, some of you will have done algorithms and data structures and graph theory in your past, and you might be at the peak of this curve. This is Mark Needham's curve of learning Neo4j, which I think those of us that have learned Neo4j have all gone through. And initially, it seems very daunting to learn a new technology, to learn something that's so biased towards a kind of computer science view of data, a kind of algorithms and data structures view, where people use terms like breadth first search and degree and centrality and so on. And it's like, oh my goodness, this takes me back to my undergraduate days. But I think you'll find that once you're over the initial hump of, oh my God, this is hard, that you fall into a kind of sweet spot of graphs where you find that lots of problems that were difficult with other kinds of databases, particularly relational databases, actually become very intuitive and straightforward with graphs. And I think there's a very good reason for that, because it turns out that we do live in a connected world. In fact, this is where I live. This is a map of the London Underground network, and even if you've never visited this fine city from where I'm broadcasting, you would be able to navigate this map very easily. Therefore, you'd be able to transport yourself around London with very little inconvenience. That's because we know the rules. You can't teleport simply from one place to another, but what you can do is follow the graph. You can follow a station along the line to another station. You can traverse this graph. So even at human scales, you can start to, you can fly into Heathrow and then visit the Neo4j office at Southwark, and you could find the fastest route here. And you can see in this case it would be to take the purple line from Heathrow and then change onto the grey line and then come down to Southwark. And even if you knew nothing about the topology of London or you knew nothing about graph theory, you would be able to find very easily a good route to our office. You would, for example, not go too far north or too far south, because somehow this notion of graph traversal is inimical to the way that humans think. So we already are able to think in terms of connected data, and we know the rules. When we apply this to other data problems, it often makes them far simpler to reason about than if we're stuck with situations like this one. Now, some of you on this call are absolutely far smarter than me, and you have the ability to see through relational schemas into the underlying intent. Over the years of working with graphs, I've kind of lost that ability, and when I see things like this, I get quite annoyed by it, because in this problem, clearly what I'm trying to express is the notion of customers owning accounts, and in this case, customers owning their own accounts. Alice has account 326, and Bob has account 981, and they clearly have a joint account 725. However, in the relational world, we are forced to pander to the database's needs. We have this join table, and this is nothing but accidental complexity. This join table only exists so the database can do its thing. It doesn't actually appear in my problem domain, so it's something that I have to manage outside and in addition to that problem domain, which is kind of annoying, right? I mean, a database should be able to conveniently and elegantly express the way my problem domain works, rather than cluttering it with all this accidental complexity. But still, you know, you're clever folks, and so some of you might already be thinking, well, you know, my database can already, my relational database can already do this. In fact, there is a book all about this, trees and hierarchies in SQL for Smarties. Well, I don't think so. I think there are problems with this approach, and I think that, you know, relational tech, while it may be solid in terms of transaction processing, and it may suit certain applications like payroll, where you know, tabular data is fine and you don't do many joins, ultimately, I think that you run into a rather enormous problem with relational tech, and it is this, expressed in terms of Diet Coke, Mentos, and a budgerigar. That is, eventually, even in the best relational schemas, you end up joining. And it turns out the relational databases aren't terribly good at joining. Cartesian product of set ensues, places pressure on main memory eventually spills over to virtual memory, pages on disk, and now your query is chugging along at disk speed rather than cache speed or RAM speed. And that's a problem, because it means the kind of ambition that we have to explore data sets, connected data sets, is limited. Because often when we're trying to shoehorn a graph into a relational store, or indeed another a denormalized store, then what we're really doing is we end up doing recursive joins. And that kind of recursive join bomb problem means that you could probably join once or twice or maybe 3 times. But as the size of the intermediate sets grow, the mechanics of the system you're working on starts to limit your ambition. In fact, this was the genesis of Neo4j, that my founders had built a graph API on top of Postgres because the SQL was too hard to write to express graph things. But once they'd written the graph API, they found they started to write ambitious graph queries which would crush the underlying engine being based on sets. And they had to ultimately remove that underlying engine and replace it with something that was native for processing graphs. So we've shoehorned a graph into a model that can't really support it. Neo4j is a native graph database, and it supports something called the labeled property graph model. Now, labeled property graph is pretty straightforward to understand. Unlike the big book you had to read to understand the relational model, you can explain the labeled property graph model in one slide. Admittedly, it's a widescreen slide, so there's slightly more data available to me. But we have the following things in the labeled property graph model. We have nodes, or vertices if you're feeling mathematical. And those nodes can have optional labels, which are like tags. They describe the role of the node in the network. And those nodes can also have properties on them, and properties are keys and values. We also have, to join these nodes together, relationships or edges for the mathematically minded. And in Neo4j, relationships are named. The name describes the role of the relationship. Then relationships are directed. They have a start node and an end node, which may be the same node. And those relationships can also have properties on them. You can have timestamps or weightings or ages or dates or whatever it is that you want on them. Meaning that when we want to describe Alice and Bob's bank accounts, we can do so very naturally in Neo4j. On the left, you see that we have customers. The red squares, the red nodes are customers, labeled customer. Oops, sorry, ignore Bob, I've kind of forgotten to update him. We have the property, Alice, and you can see that Alice has an outgoing relationship named owns to two other nodes labeled account. And you can see that Bob has an outgoing relationship named owns to two other accounts. Now, if you wanted to find Alice's total position, it's very straightforward. You would traverse over the outgoing relationship labeled owns to the account that Alice owns and sum. Equally, if you wanted to find out who the owner of an account is, you would pick a particular account and then you'd work backwards along the owns relationship to find who the owner is. And what's important is in Neo4j, whether you traverse tail to head or head to tail of those relationships, the performance is constant. It's an order 1 algorithmic operation, and it's mechanically super cheap. On my laptop, for example, and it's just a regular dev laptop that I'm presenting from, I can traverse about 14 million of those per second on an untuned instance of Neo4j. Yes, it's a lovely laptop. It has lots of RAM and it has an SSD, but it's just a laptop. So that's our model in a nutshell. We have nodes, relationships, labels, and properties. And you can bring all of those together to build very sophisticated data models. You can build large graphs out of those primitives. Then the question arises, well, how do I query the graph? And for that, Neo4j has a query language called Cypher. And Cypher is intended to be a humane query language. It's intended to be accessible to non-specialists. In fact, the genesis of Cypher is a reformed SQL DBA called Andres Taylor. And when he first built Cypher, the first early versions of Cypher some years ago, he wanted it to be something that was accessible to non-specialists so that non-specialists could access the power of the graph. And in order to do that, he wanted to close the gap between what you draw and what you store. So here we have this simple human relationship. We have Anne and Dan, and we see that Anne loves Dan. We have no idea whether Dan loves Anne in return, but we know that Anne loves Dan. And if you were to realize that scenario in a graph with nodes and relationships, it might look a bit like this. We'd have a node that represents Anne, a relationship from Anne to Dan, and then a node that represents Dan. And that's fine. That's something I think that's quite intuitive. It's a bit sad because you probably would like to see Dan reciprocate. So then the question is, given that we have this graph, how would we express that in the query language? And I think this is one of Cypher's most wonderful intuitive leaps, is that we express that graph pattern in ASCII art. So in this case, what we see here in the ASCII text is the parentheses represent nodes, and the kind of square brackets represent an arrow. And what we're trying to get at here is kind of Visio art. So if you can draw a picture in Visio, you can write a Cypher query. And in fact, this says legal Cypher syntax. It's a node representing Anne with an outgoing loves relationship to a node representing Dan. And then finally, if I wanted to turn that into a query that I would type into Neo4j, or my application would issue to Neo4j, it would end up like this. And what this reads as is, on the left, a label person, so a node labeled person, with the following properties: a key, name, and a value, Anne, has an outgoing love relationship to a node labeled person, which has some properties where we have the property name, key name, and value Dan. So this is find me where Anne loves Dan. Now, if you can draw ping pong balls and wires, if you can draw circles and arrows, you can start to specify, you can start to write Cypher queries. You can start to, in this case, explore simple social networks. And then all you have to do to take that Cypher pattern and really make it a legal Neo4j query is to wrap it in the appropriate keywords. So if we were to take this query here, match person and loves someone, then return that someone, that whom, we would find who Anne loves. And the database would do this as follows. It would, the match keyword says, hey database, I'm looking for this pattern. I'm constraining part of the pattern to a particular node where it must be labeled person. It must have a property key name, and key value, and it must have an outgoing relationship loves to something that isn't constrained. Tell me all the places in the data set where this matches. And it may be, of course, that multiple things come back from this query. It may be that we find Dan because we know Anne loves Dan, but Anne may also love movies or pets or painting or driving Formula One cars. So we'll find all the things that Anne loves. So querying Neo4j is very, very straightforward. Towards the end of this webinar, we're actually doing some live coding where we build a retail recommendation system in 5 minutes, showing just how powerful this stuff can be. But one of the asks that Demi gave me in designing this webinar was also to talk about some of the underlying tech, because not only might we be users of Neo4j, but we're all technologists too, and sometimes it's a little bit interesting to see what's going on under the covers. So of course, when we're executing this Cypher query, we don't just execute it verbatim. Not at all. In fact, the Cypher query will go through several levels of cost-based evaluation under the covers. So the Neo4j query planning engine will actually pick the best underlying traversers for you. It will rewrite the query on the fly, so it gives you the lowest cost operators. It will sample the query, cost of the query, and it will rewrite for you so that queries can be faster than even native Java code using the low-level Java APIs. And the query optimizer and query language pipeline will also bind at a very low level in the Neo4j stack, which is unsuitable for normal humans, but gives you a high degree of mechanical sympathy. So while you can write very high-level queries, like this one, for example, this is actually a social recommendation query that we'll see more of later, you can write something that's relatively human-friendly, and under the covers, the database will optimize that query through rewrites. It will optimize by picking the appropriate traversal pattern through the graph at the current time using runtime statistics and a whole plethora of other things to make sure that you get absolutely astounding performance, like wow. And it's not just us that think this, right? I mean, the kind of feedback we get on Cypher is that users absolutely love it. It's a very, very powerful language to get to grips with. There's not much to it. The heart of Cypher is that match clause where you're literally drawing pictures about what you want to find, and then the rest of it is just dealing with the hits that you get from your underlying graph. It's if you have SQL already in your fingertips, you should find moving to Cypher a relatively small thing. The other thing to know about Cypher is that it isn't any longer restricted to Neo4j. So there is a standards body called OpenCypher, which has participants from a whole range of companies, including some other tiny little database company called Oracle and some little startup thing called Spark, where all of these folks are committing to support a future version of Cypher. So it will be, imagine Spark, Cypher on Spark, for example. So any learning you do in Neo4j Cypher will enable you to do graph operations in the future on a whole bunch of other Cypher-aware applications.
Jim, a
So that's the
small
query.
question.
Of course.
Meaning that Open Cypher should be like incorporated with Spark X, or how is the integration going to work?
So the integration is ongoing. There is already a Neo4j Spark connector that Michael Hunger wrote, but I think in the long term you will see that Cypher will be the default API for graph work on Spark. So it will be the default API for example, GraphX, and that's what
Meaning,
the Databricks folks and some Neo4j folks are currently working on.
meaning the language or the actual API is going to change to be like Cypher compatible or something?
Meaning the language, so this will be Spark that will
I see.
understand Cypher. And you can imagine,
Okay.
I talked about this somewhat at my Graph Connect keynote. You can imagine in some future scenario, actually the cost-based optimizer could actually make a call on whether to ship your rewritten optimized Cypher query to Neo4j for completion of a query, or whether to ship it to Spark for completion of some computation. I think that
I see.
having a common API in the form of Cypher the language makes that eminently doable.
Okay, great.
Cool. So that's the query language level. I'm now going to come down a level. So we're going to head from the query language, which sits at the top of our stack, down towards the disk. And so then it kind of begs the question, well, what does a graph database need to do? And the kind of slightly facetious answer is, well, it needs to write graphs and read graphs. Okay, done. End. Thanks for listening. No, kidding, of course. Absolutely kidding. There's a little bit more to it than just read graphs, write graphs, and in particular, a good graph database needs to be able to write graphs safely and read graphs quickly. And I think those two adverbs are super important. They are it's not simply when you're picking your kit, it's not just about a feature comparison, a kind of functional feature comparison. Actually, because you're trusting your data to this software, you need to know that your data is safe. And one of the ways that Neo4j deals with that is that Neo4j is an ACID transactional database. While all of the cool kids were off doing eventually consistent things, Neo4j remained uncool. We remained an ACID transactional database, which really means that once you write in Neo4j, once we've act a write, your writes are there and they will not be lost. How do we do this? Well, actually, this is quite a standard thing in databases. We write commands to a log, to a write-ahead log, and then periodically, which is flushed, and then periodically we make sure that we rotate those commands over into the query model. So what that means is once your commands are written into the write-ahead log and the write-ahead log is flushed to disk, that you are durable in one place, and then that your write can be safely act. In terms of how Neo4j works in the transaction subsystem, in Neo4j transactions themselves are in-memory objects. And what happens is our lock manager takes locks on the various nodes, relationships, properties, and so on in the read model. If the database is committed, we add those commands to the write-ahead log and we flush. If the transaction is going to be rolled back, we simply release the locks and we just nullify the transaction object. So it's actually a very simple mechanism inside. But here's the thing: write-ahead logs are wonderful things for safety, but write-ahead logs can be a point of contention for multiple threads. And of course, as a database, we fully expect that we will have multiple concurrent users because it's the 21st century. However, the write-ahead log is a place where things are naturally serialized because we want one log entry at a time, and we can't have concurrent writers overwriting one another's commands. That would be a recipe for disaster. So the way we've implemented this in Neo4j is a very mechanically sympathetic thing, which is that we have a single writer thread. So lots of concurrent contractions can be going on all at once, but there's only a single thread that takes those transactions and pushes them into the log. Now, there's a natural batch window that appears, so you can have by number of entries or periodically or what have you. What that gives you is that we amortize the flush latency over a number of transactions. This means that for fine-grained transactions, especially, which would normally have a relatively large flush time relative to the amount of user work they do, we can now amortize the cost of that flush, particularly if it's a mechanical flush on a spinning disk, across many transactions. On my laptop, with this enabled, running a fairly naive benchmark, I went from about 5,000 transactions a second up to about 30,000 transactions a second. So kind of an order of magnitude change by allowing Neo4j to intelligently batch my writes down to the log, which is pretty cool. This does not.
It's actually a configuration?
No, that's automatic. Now that went into the code base in Neo4j 2.2. This does not in any way reduce the ACID properties, because you still will not receive, your thread will still not receive an ACK that you're durable until you're durable on disk. It's just that your transaction will likely be made durable on disk alongside several others. So there's a trade-off there of latency for throughput. But given the latency might go from fractions of a milliseconds to milliseconds, we think on the whole that's a very, very good trade-off, because the throughput of your ACID transaction goes up dramatically. So once we're out of the log, we're then into the store files. And the store files are really where all of the action is in terms of reading Neo4j. So one thing that we do in Neo4j is that we are very, very keen to separate graph from data, or structure from property, if you like. And the reason is that we optimize for fast traversal performance in Neo4j. We do not optimize for fast lookup of user data, of those properties, of those phone numbers and names and MP3s or whatever else it is that you're storing in Neo4j. Because an idiomatic query in Neo4j uses the graph structure to locate the points in the graph from where ultimately you would want to read that data in. We don't. An idiomatic query in Neo4j is not taking all the property data from all the nodes and relationships you encounter. Now, in order to get this fast traversal performance, the graph structure parts of the query of the store are in fixed size record format. This means that effectively we have a fixed size address space, and that we have a fixed size pointer into records in that address space. Now we observe that simply by following pointers through that address space, we are performing a graph traversal. Now, if you look at the record layout here, this is Neo4j 2.0 layout. 3.1, which I'm currently working on, the records are slightly larger because we've increased the addressable size from 60 billion up to a quadrillion. That's not a number that people normally use, but a quadrillion graph objects. And the way that we traverse in the graph is that we follow these relationship chains through the record store. Each one is order one, algorithmically order one computation. We multiply record ID by record size, and that gives us an offset into that file. That is ridiculously fast to look up, unless you're on a spinning disk with very little RAM to cache, in which case it's annoying. But on modern computers, that is ridiculously fast. So your traversal complexity is order n, where n is the number of nodes relationships that you touch during the traversal. And of course, a good Cypher query will minimize that. You can minimize that in terms of the way you express the query, and our optimizer will also minimize that. That, by the way, it's worth mentioning at this point, that means that Neo4j graph queries do not grow proportionally to the size of the database. Neo4j graph queries latency is proportional to how much of the graph you choose. This plays into an interesting trade-off here. Right? Traversing a relationship in Neo4j is algorithmically order 1. This is a property called index-free adjacency, coined by Neubauer and Rodriguez in 2010. And what they observe is that a node has incoming and outgoing relationships, and those incoming and outgoing relationships kind of serve as a mini index for other nearby nodes that you might want to traverse to. So you don't need a global index when you're traversing a graph, because at each point where you reach a node, you've kind of got some other roads you can take to other places you might visit. Those traversals are order 1. If we've got a global index over the graph, then those traversals would be n log n. And log n, even for a modest number of graph objects, a billion or so on, log n is enormous, right? It's like 12. That sucks. So n log n for any reasonable production size database is going to be vastly more expensive than just order n, which is what Neo4j gives you. So what about on the read channel then? Well, there's more to the read channel than just the store files, although they are super important. But we actually, on top of that, we have some caching infrastructure, we have our locking manager, and then ultimately we have the APIs that sit on top of that, both programmatic APIs, remoting APIs, and things like our query language Cypher. In the read channel, we cache because we know that disks perform badly, even spinning disks, or especially spinning disks. But generally speaking, we prefer CPU cache, and we prefer main memory to any kind of disk. We don't want to have to go over a separate bus. From Neo4j 2.2 onwards, caching in Neo4j is done in an off-heap cache. We're a JVM server, but our caching is off-heap. And the algorithm we've chosen is an LRUK cache. LRU we're all familiar with, it's least recently used. But LRUK is an adaptation of LRU, which also takes into account popularity. So if 2 pages are both candidates for eviction, the algorithm will check which one of those pages has been historically most popular, and it will keep that one. And the LRUK cache authors in the literature have demonstrated that this is statistically the most optimal caching strategy you can come up with. Because of this caching strategy, on my laptop, and as I said, it's a decent dev laptop, but it's a laptop, we can get steady state traversals of about 3 or 4 million traversals per second per core, which when I sum it up on my laptop is somewhere in the region of 12 to 16 million traversals per second in the aggregate, which is, you can explore an awful lot of graph at that kind of speed. So that's the read and write channels, but of course, what happens when we want to come up one layer still and say, well, that's one instance of Neo4j, how do multiple instances of Neo4j function? And actually, we have an existing clustering topology. It's very much like the way MySQL clusters. We have a master-slave scenario whereby we use the Paxos algorithm to elect a machine in the cluster that's going to play the role of master for a while. And then we have slaves which are kept up to date with respect to the master. Our slaves are currently kept up to date by log shipping. It's a system very similar to Apache Kafka. Each slave is eventually consistent or asynchronously replicated with respect to the master, which means that they are AP if you're picking from CAP. Slaves can also be optimistically pushed to. So slaves will poll for transactions that they have that have been applied by the master, which they need to apply. But equally, when a master receives a transaction, a write from the user, it can also push transactions directly to usually a subset of the slaves. And this mechanism has served Neo4j very well for several years. But of course, the science of transaction processing, particularly in the academic literature, has moved on enormously. You could be forgiven for thinking transaction processing had died in 2007 when eventual consistency became the norm. But from around 2012 onwards, the academics picked themselves up, dusted themselves down, and started doing some pretty amazing things about very, very high performance transaction processing. So what my team works on and what will be released in the coming weeks at Graph Connect in San Francisco in October is something a little bit different, something that will enable causal consistency at a scale in an architecture that we call core edge. Now, in core edge, the clusters, the machines in a cluster have one of two roles, core or edge. Core machines are immediately consistent with one another via a protocol called Raft. And Raft is very similar to Paxos. It's a non-blocking consensus protocol, but it's a wee bit simpler than Paxos, which means, importantly, when one is building distributed algorithms, there are fewer places for bugs to hide. And what Raft gives us is guaranteed safety with a simple majority of servers. So if a simple majority of servers acknowledge a transaction, that data is now safe. And unlike Neo4j, existing Neo4j HA, we use the Raft protocol to actually transact data rather than just make a decision about who is the master. So there is no data loss after failure. Even if a majority of the cluster is disabled, is switched off, then the cluster will revert into a read-only mode. So it's a very, very safe place to store your data. If you then add edge machines into this cluster, you actually get something really interesting in terms of being able to scale it out. Core makes your data safe. Edge makes your data scale. Now, edge machines are effectively caches, but they're not dumb caches. They are fully fledged Neo4j instances where you can run arbitrary graph workloads. But they are read-only, and they do not have permission to, they are not allowed to have an opinion about the cluster topology. They are not pets. They are not special. They are nothing but cattle. And Core Edge is designed to run hundreds or many thousands of these edge servers to scale to very large graph workloads. Just like in Neo4j HA, the transactions are propagated via log shipping, kind of Kafkaesque log shipping. So you've got this nice split between the core, which is safe, and the edge, which is scale. Now, you might ask the question, how do I reason about this? Well, in a simple deployment architecture, you might have a system very much like this, where you've got, it's multi-data center, you've got the core cluster in one data center, and then edges in your other data centers for localized graph read workloads, or read-heavy workloads. Equally, you could spread this, you could spread your cluster more fairly around data centers. You could put some core in each of them. And you might initially think, well, that's a bit silly because now you've got, when you do writes, it has to go across the WAN. But one of the nice things about the Raft protocol is that we only need a simple majority of machines to respond before we can consider the data written. So if you have a data center that's very remote from you and data centers that are nearer to you, you only wait for the fastest data centers to respond, or the fastest instances in those data centers to respond before you consider the write written. Now,
Jim, I
what
have
about
a small question about the
Sure.
last slide, actually. Meaning that this kind of architecture, is it like sharding or replication between the data centers? The
so this is
edges are more like replica sets, probably, right?
These are replica sets, absolutely. So in this version of Neo4j, Neo4j is a single image database, and of course the reason for that is that we use pointer chasing through a single address space in order to provide traversal performance. Now there are techniques like cache sharding that you can use to optimize individual instances so that they're always hot. The caches are always hot for your queries, and in fact, Neo4j through the driver stack will try to do that for you automatically. And I'm about to come on to causal consistency, where I think that's a good chance to explain that in a bit more depth.
Okay, great.
So, oops. So oops, sorry, I want to go back here. So we don't take chances with your data. Neo4j has never been a kind of database where your data is left to chance. I suspect some of this is because we were founded in Sweden, and the Swedes are super conservative when it comes to things like that. Look at the number of airbags on a typical Volvo. We are all about safety. So we don't play dice. When you write to Neo4j, when you write to Core Edge, your rights are written. And when you get an ACK, it means that you are durable, or in the case of Core Edge, multiply durable, such that failures mean you will not lose data. But at query time, you can actually start to think about which level of consistency suits you best. Now, here are the possibilities. I think the default one for this will be read your own rights edge, so number 2 on this slide. And what that means is that when you perform your writes, you'll write into one of the core instances. And when you perform your reads, you'll read from one of the multiplicity of edge instances. But what we've done in Core Edge is we've actually made it so that the database itself supports this reasoning about where to read from, ensuring that your rights are there. And so we've actually implemented a scheme which is very similar to HTTP e-tags, but based on Neo4j transaction IDs. So Neo4j has strictly monotonically increasing transaction IDs. And what that means is effectively an integer or a long that always increments. What that means is when you write into the database, and the database drivers will guide you towards an appropriate core instance for that, you'll get transaction ID back, or the driver will get transaction ID back. And if you specified that you want read your own rights consistency, when your subsequent read queries go to a core or another, or more likely an edge machine, they will take with them that transaction ID, and the query will then be run at or beyond that transaction ID, meaning that you will see a copy of the data set, which includes the activity that you have executed against it. This means that actually it's very easy to reason about this database. If you set a particular consistency level, you can always read your rights, which I think simplifies greatly, at relatively low cost, simplifies greatly your interaction with the database. No more do you have to deal with the uncertainties of eventual consistency. The database deals with that for you, and all it means is if you encounter an edge server where your right hasn't propagated yet, your query will be held up momentarily until those transactions have been shipped over via log shipping, and then your query will be allowed to run. Now, what this also means, given this architecture, is that it's actually possible to implement a whole range of consistency options, up to and including linearizable, which is the holy grail of distributed computing, where multiple distributed interactions can form a single serialized timeline, which makes things very, very easy to reason about. How do you query this database? Well, in Neo4j 3.0 onwards, we support a new binary protocol. It's called Bolt, and the drivers for Bolt, in fact, from where I sit, I can actually see the drivers team beavering away on this. They actually allow you to declare the consistency level that you want, and then they deal with everything for you. They deal with all of the topological requirements of finding a good core server, a good edge server for you, and then actually it will deal with this read your own rights in core edge servers on your behalf. So it's very easy to reason about in your application, and actually, given the mechanism just piggybacks on the existing transaction shipping stuff, it's not expensive in the database. So read your own rights is not an expensive operation in Neo4j Core Edge. So it's very easy to reason about, and it scales well. And we'll be opening the floodgates to this at Graph Connect in San Francisco in October, where we'll be advertising our beta program. In the meantime, if you are desperately brave, then of course Neo4j is an open source database, so you can always take a look at our GitHub and see what we're doing there. So we've got a few more minutes left. I would like to show you a quick demo for real-time recommendations. So let me just do that. Great. So hopefully now what you can see is Neo4j console here running in the browser, and I'm going to ask the database if it's got anything in it. We see this database is empty. That's great. What I'm going to do is I am going to fill this database, and I've got a little bit of data that I've pre-canned. I'm just going to whack it in here. So I've just loaded a bunch of fake data. Let me show you what I did there. So I created some nodes, and these nodes represent products that you might buy in a supermarket. And in this case, I said, hey, database, create me a node. That's the round brackets. Give this node the variable name bread. Label it as a product, and give it some property data, a stock keeping number, and in this case, an English description. And I've created a few of these. This is not representative of a real supermarket, but you get the idea. And then I've created some links between that data. So for example, here, I've created a link between the node that represents bread, and I've said that that's complementary to butter. If I'd localized it, of course, I now realize that would be hummus, but bear with me. And this kind of data isn't usually generated by humans. It could be generated by domain experts, but more likely this kind of data is generated by machine learning. So it's looking for things that are often bought together, so toothbrush and toothpaste and so on. Then the next bit of data that I've created is some data about some users. And of course, in supermarkets, users identify themselves via loyalty cards. In online supermarkets, they identify themselves by username and password, so you get that data very easily. And then I've got a bunch of basket data. And the way that I've modeled baskets is as a linked list. So these are effectively baskets that contain a set of purchases. And you can see here that Alice bought this basket. She saved this basket, and she's currently working on a third basket, B3. So there's a linked list of Alice's purchase history, and we've got some statuses about what she actually did with those baskets. And we've got the same again. We've put some items in those baskets, and we've done that several times for several other customers. Fine, all the way down. Finally, we've got one set of data which is a little bit fake. I've just said that the supermarket somehow knows that Alice is friends with Bob and Dora and some other people. That's not how supermarkets work in reality. In supermarkets, in reality, they work with demographics. They know that I'm a middle-aged white guy that lives in London, and they therefore know the things to recommend to me because we're quite homogeneous. But for the purposes of this webinar, we're just going to pretend that this kind of fake social network data is good enough. And of course, that's all written in Cypher, in Neo4j Cypher language, and it's pretty easy to understand, right? I've got nodes and relationships, and those relationships are named and directed. It's kind of easy peasy. So then the question arises, well, what can I do with that data set? And in fact, let's have a look at that data set again, right? So that's database. Find me all nodes and return all nodes to me. You can see now, in here we've got these blue nodes that represent products. We've got these red nodes that represent baskets. We've got these green nodes that represent our customers. And you can see that we've got this basket which contains these products and so on. So cool. So what can we do? Well, one of the things we might do as the supermarket is just say, well, what are my top 5 products? So let's run that. And I'm going to turn that actually into rows. It's a bit easier to understand. Then I can find that my top 5 products are milk, bread, pasta, butter, and tea bags. Of course, tea bags because it's a British supermarket. But then what we're actually doing here, saying, hey, database, find me a node labeled customer where they bought something. This is a basket, and where some product was in that basket. Return me the product. Return me the count of the product, ordered by the count of the product in a descending fashion, and just the top 5. And that tells me the top 5 most bought products. Now, this isn't a massively interesting query. I mean, the supermarket might find this vaguely useful, perhaps in order just to top up, make sure that its supply chain is working well for its most popular products. But perhaps a more interesting query and I actually was subjected to a query a bit like this today when I did the office snack shopping, is what are my top 5 products? And in fact, the top 5 products that I was recommended were like loads of chocolate bars because I did the snack shopping for the office. So actually, this is far more interesting. Similar kind of thing. We're saying, hey, database, find me this pattern where I've got a customer that bought some basket and where I had products in that basket, but where that customer's name was Alice. So this is the logged in user or the current user at the checkout or whatever. And then return me the product, return me the count of products, ordered by the count of products in a descending fashion, limited to the top 5. So this is telling me Alice's top 5 products. And what I do with this is say, well, Alice has only got 3 recommendations: butter, sliced bread, and toothpaste. But if Alice ever came to our store and didn't buy any of these, we should definitely be recommending them to her because they're very, very popular. Now, what else might we do here? Well, we say, actually, you know what? Humans are fallible people. And you know this, right? Because, I didn't need the iPhone 6S. I had a perfectly reasonable iPhone smaller number, but then I saw someone else with a 6S and it's like, oh, must have. So there's this notion of social pressure that we can exploit in selling, and in fact the online retailers know this too well. So what does a social selling query look like? Well, actually here you can see there's kind of 2 parts to this query. The first part looks a bit new. It's saying, hey, database, find me some customer which has an outgoing friend relationship at depth 1 or depth 2 to some other customer. And so this is friend or friend of friend. Notice we're not afraid of this star here. This doesn't imply any relational joins or Cartesian product of sets or any of that. This just is pointer chasing. And we're saying where that customer is Alice and the customer and the friend are the same, because of course friend of friend could be me. I am your friend. You are my friend. I want to exclude myself from this query. I want to make kind of a donut pattern around me. With the friends that we find, so with the social network that we find, then we're back into our kind of regular recommendation query, which is where the friend bought some basket, which had some products in it. Tell me about the product, the count of the product, order by the count of the product in a descending fashion, and limit to 5. So give me the top 5 products that my friends and friends of friends have bought. If I run that, Alice's friends and friends have bought quite different things to Alice. They bought milk, bread, pasta, tea bags, butter. So now Alice knows that if her friends are coming around for dinner, she needs to buy all of these things, otherwise she won't be, she'll feel a lot of social anxiety that she's not exactly the same as all of her friends. Of course, this is a rather hilarious use case because no one's really going to be anxious about the butter they're going to buy. But if you notice on aggregate that people like you are buying iPhone 6Ss or people like you are buying Dell laptops, then the retailer that you're interacting with certainly should place them prominently as recommendations for you when you're interacting with their site. So then finally, in fact, this has somewhat amusingly to me anyway, is the query that brought me into Neo4j. And it is recommendations for customers based on those complementary products. That is, if a customer has already bought one thing, what can we upsell them that would be equally useful? So again, we're going to run this query and we're going to see that Alice should be buying bread, unsliced bread and butter based on her previous purchases. Or based on her current basket. So this is saying, hey database, find me some customer who has an outgoing current relationship to some basket where I've got something in that basket which is complementary to some other product. Where that customer happens to be Alice, the currently logged in customer, tell me about the complementary product. So if a customer's got something in their basket, tell them about the things that go well with it. And I initially fell into Neo4j in 2008 because of exactly this. I was working on a product catalog system for a telecoms company where I wanted to tell customers what other things they could buy based on their existing purchases, based on the existing hardware they had installed in their homes, the phone service that they had installed, the video on demand packages that they had, and so on and so forth. And what this provides is exactly that. In 2008, when I came to write the equivalent of this query, it wasn't 3 lines of Cypher. It was a 3 to 5 year project where we would take specialized off-the-shelf software and then customize it. And then when I found Neo4j could solve this, not in 3 lines of Cypher, but in not very many more lines of the Java API, since Cypher didn't exist then, that was an absolute win for me. So actually, it made my life an awful lot easier. So where are you guys going to get started? You've already come to this demo. There are lots of great books out there that you can use, including the O'Reilly Graph Databases book. There's just an absolute mountain of good Neo4j books out there right now. The O'Reilly Graph Databases book is available as a free ebook. So if you go to graphdatabases.com, you can get the full version of that ebook in exchange for your email address. And despite the fact that I wrote a bunch of it, it's still a really good book. So that will help you, I'm sure. The Neo4j community is also super welcoming. We run a really friendly mailing list, a really friendly Stack Overflow community, and so on. So come participate. And don't be afraid of Neo4j perhaps it even being slightly new to you. Graph Tech is still, you guys on this webinar are still relatively early adopters, right? But there are people who've trodden this path before you, including household names and people that you might think are relatively conservative. But there's a whole bunch of people, including local to you guys in Israel. eBay spring to mind as a prominent Neo4j user there. So you're not treading an untrodden path. There are lots of people that have been there before you, so there's lots of people that you can turn to for advice and help, including us at Neotech on making your Neo4j adventure a success. So that's all I've got for today, but just leave you with one Admiral Akbar inspired comment, that when you do have a data problem, 9 times out of 10, it is a graph. And thank you for listening. Super happy to take some questions, and equally happy to take questions offline via Twitter, email, blah, blah, blah. So Demi, do you have any questions for me?
Yeah, actually, I have a question that somebody asked. Can a relationship change over time? And if so, what would a relationship migration look like?
Sure. So actually, logically speaking, sure, relationships can change. You can write Cypher that deletes relationships and adds new ones. At the moment, I happen to know as an implementation detail that we would delete one relationship record and replace it with another one. But from your point of view as users, those relationships are quite mutable. And in fact, if you think about it, in a graph, you would expect those relationships to change over time as you find new friends in Facebook, and you get sick of old friends, and so on and so forth. And Neo4j supports that very. It's a normal part of Neo4j.
Mm-hmm. And I know that you have much experience in lectures, so most of the times you have that annoying person who sits in the first line and asks lots of questions. So I'll be that annoying bastard right now, and I'll have some questions that I know that many people have asked me. Let's say one about a UI workbench for Neo4j, something to visualize things, some kind of tooling. Can you recommend something?
Yeah, so look, I mean, you saw just the tip of the iceberg in terms of what the Neo4j tooling can do. So Neo4j comes with the Neo4j browser, which is a very developer-centric tool, and it's really great for when you're prototyping queries and so on. As you go more towards business-oriented users, there are a bunch of frameworks out there that support visualizing graphs, things like Linkurious, things like Keylines, things like Tom Sawyer. Things like, and then if you want to roll your own, there are things like D3 and Zoom charts and so on. So there are a whole bunch of things that you can do. But I think a good starting point for that is definitely the Neo4j browser. It actually is very, very useful, particularly if you're a developer building with Neo4j.
Yeah, and another question about DevOps, operations, monitoring. Once you have let's say a single source of truth or something that you rely on, and you need to monitor it, and you need to have visualization over the infrastructure. Do you have some kind of tooling for that at Neo4j?
Oh yeah, absolutely. So the wonderful thing about Neo4j is that it's operationally very boring. That 4j thing, which I think is an awful name to be honest, but what it implies is that we're a Java stack. And so I would say this: if you can run Tomcat in production and you have the infrastructure for plugging Tomcat into your monitoring software, you can just as
like
easily.
JMX? Do you hear me, Jim?
Say again?
Like JMX,
Absolutely. So
connecting
we've got
it.
JNet, we've got HTTP. So there's a whole bunch of plumbing endpoints that you can plug in. It's super operationally boring, which is the way a database should be.
It's great. A great method to work with. And another question about where to deploy Neo4j. Most of the deployments are on-prem, or you have cloud-based, like something on AWS or on Google Cloud Platform.
Yeah, so Neo4j can be deployed anywhere. It's just a Java app after all.
Hmm.
Inside Neo4j, we use a lot of AWS for our testing because it's really easy to kill databases and harm them. I'm going to guess a little bit here, but I would imagine that about half of the Neo4j customers are using cloud providers, and half the Neo4j customers have their own on-prem solution. I should also
Hmm.
draw your attention to a bunch of Neo4j partners who are themselves cloud providers, so the likes of GrapheneDB, GraphStory, and so on, that actually provide Neo4j in the cloud services.
So you have actually like paid Neo4j services, right?
Yes, third parties have that. Neo4j itself,
Yeah,
we just build the database, and third parties have Neo4j in the cloud services that you can choose to rent.
I see. Great. And another question about best practices or tuning manuals or some kind of resources that you'd like to point out, some kind of tech blog about pointers for people who start using Neo4j right now.
Absolutely. So, I mean, the undisputed source of truth for Neo4j tuning is the Neo4j manual, which is actually a really nice piece of kit. The
Hmm.
other blog, the blog that I would point you at, again, I think is an unofficial source of truth, is Mark Needham's blog. And when Mark learns something about Neo4j, he writes it down. So definitely tune into that one. As
Sounds
and
great.
when you get into a situation where you're thinking about production with Neo4j, talk to us because we have between us many decades of experience of
Hmm.
Neo4j into production, and we can often give you some tips, tricks, hints to make sure that your path to production is as smooth and unremarkable as possible. We like boring production systems because all the excitement is in the graph.
Because they tend to work.
Yes, absolutely.
Yeah, and the last question that I have actually, because I see another question popped by someone. Is there any encryption features in the right API, for example, encrypting a relationship or a node attribute? For example, in the US, working with healthcare data would require HIPAA compliance.
So in the version of Neo4j that you can download today, there is not. But of course, there are two things here. There's nothing to stop you from running Neo4j on an encrypted file system, nor is there anything to stop
Hmm.
you from writing your own encryption scheme for particular properties that need to be kept confidential. And in fact, using Neo4j procedures, that actually becomes a native part of your Java of your Cypher API. You could write a procedure that's literally encrypt according to whatever encryption standard you needed, and you could wire that into Cypher, and it would just look like a normal Cypher function from everyone else's point of view. In the
Yeah,
future,
just
in the 3.1 roadmap, which I believe has been relatively widely announced, there are several more security features that move us in that direction.
hmm I see. So another question. Okay, no, just people saying thank you. And my last question is actually about the whole clustering and the sharding part. As we said, as you like described there, Neo4j is like a single node database which replicates with other places in DCs, and the availability is like enhanced with edge nodes, right? If I'm not mistaken.
The scalability is enhanced. The ability to
Hmm.
perform work is enhanced with edge nodes, yes.
Yeah, but like the data is located in each data center as a whole. It's not sharded between data centers, right?
That's correct. Each instance, each core or edge machine will have a full copy of the database.
I see. That's awesome. You've answered all of my questions, and I don't see any other questions in the pipeline. Jim, I would like to thank you very, very much for your time. It was really fascinating. I learned a lot. And people, I think, can tweet to you or contact you via LinkedIn or something if they have any other questions.
Absolutely. So I realize that a webinar is a bit of a one-way broadcast. So folks, thank you so much for giving up your evening to listen to me rant at you from another continent. And if you do have any questions or feedback, please do tweet me, or I am jim@neo4j.org if you want to do something slightly more private.
Thank you very, very much, and have a great evening, and we'll be in touch.
Thanks, everyone. Bye-bye.
Bye-bye.